8B hydraulics and fluid flow. 8.6 Pascal's principle. The octopus is among the most intelligent invertebrate animals. It also has excellent eyesight and sophisticated defense mechanisms. One of these mechanisms is the ability to move rapidly away from harm using a process similar to that of a rocket engine. The octopus draws water into an internal cavity and then rapidly shoots the water out through its siphon, a tube-like structure. The muscular force exerted on the water in the cavity is used to accelerate the octopus. This action is similar to squirting water out of a full sports bottle. The force applied to a contained fluid in one location is transmitted through the fluid to another location. This observation was first explained by Blaise Pascal. In a famous experiment, he attached a long, narrow pipe to the top of a tightly sealed, water-filled cask. A relatively small amount of water that filled the long tube above the cask provided enough pressure to burst the cask's staves. From his experiment, Pascal reasoned that changes of pressure on the surface of a confined fluid are exerted equally throughout the fluid and at all points on the fluid's container. This statement is known as Pascal's principle. Several conditions must exist for Pascal's principle to be true. First, the fluid must be confined in a completely enclosed container. If not, any change of pressure would cause it to move out the opening, similar to the sports water bottle. Second, the fluid must also be incompressible. In other words, it cannot absorb pressure changes by allowing its particles to be squeezed closer together. For practical purposes, the only real fluids that approach this condition are liquids. Gases are far too compressible to completely obey Pascal's principle. 8.7 Simple hydraulic machines. The most common application of Pascal's principle is found in machinery, such as vehicle lifts in auto shops and brake systems in cars and trucks. These devices produce a mechanical advantage by magnifying a relatively small effort force on a confined liquid to produce a much larger force that does the work on the resistance. These hydraulic machines serve the same function as the simple machines discussed in Chapter 7. Since the active medium transmitting the force is a liquid, these machines use the principle of hydraulics. To illustrate how hydraulics works, let's examine the basic function of a hydraulic lift found in an auto shop. The support on which the vehicle rests is connected by a vertical rod to a large diameter cylindrical piston. See Figure 8-21. The rod penetrates a hole in the end of a smooth cylinder in which the piston slides. This is the resistance, or load, piston and its cylinder. A strong pipe connects the load cylinder to a smaller diameter cylinder containing another piston. This is the effort piston and its cylinder. A rod connected to the effort piston penetrates the end of its cylinder. The entire system is filled with hydraulic fluid, a kind of low-viscosity oil. The effort pressure is delivered by a hydraulic pump, which may be hand-powered or part of a motorized pumping system that includes the effort piston and cylinder. An electrical hydraulic pump is standard for powering lifts that involve large distances. According to Pascal's principle, the hydraulic pressure is distributed uniformly throughout the lift system by the hydraulic fluid. Therefore, the pressure generated by the hydraulic pump, the force it exerts on its piston area, acts on the face of the larger load piston. Through hydraulic pressure, a larger piston face generates a larger force to lift the load. F equals PXA. The ratio of the load piston area to the effort piston area is the IMA of a hydraulic machine. This calculation is very similar to the way IMA is calculated for simple machines. By increasing the ratio of the load piston to effort piston areas, we can reduce the effort force needed to do a certain amount of work. 8.8 Flowing fluids. You know that liquids and gases have the ability to flow. But what causes them to flow? According to Pascal's principle, when an external force is exerted on a contained liquid, the resulting pressure is transmitted equally throughout the liquid. A water pipe in your house illustrates this principle. As long as the pipe's boundary is intact, the pipe's wall exerts the same amount of pressure on the liquid as the liquid exerts on the pipe. Newton's third law. When the water is not running, all forces are in equilibrium at every point in the liquid. Thus, there is no motion of liquid inside or across the boundary of the pipe. Newton's first law. When you turn on the faucet at your sink, you create an opening in the pipe system, which results in an unbalanced force. The water molecules accelerate in the direction of the unbalanced force, Newton's second law of motion. Because water is fluid, it easily moves around and through the bends and turns of the pipe and faucet valve parts. After the faucet is open, the water flows, due to the pressure difference between the water inside and the water outside the faucet. The unconfined water flows from a region of high pressure to one of lower pressure. The rate of flow is proportional to the difference in pressure. So the larger the difference in pressures, the greater the rate of water flow. Liquid flow rate is related to many other factors as well, such as pipe size, liquid density, liquid viscosity, and how smoothly the liquid flows. But these conditions are generally secondary to pressure difference. When the water leaves the faucet, it no longer experiences the confining forces of the pipe, and it enters free fall under the force of gravity. Gases flow because of a difference in pressure as well, but their behavior is influenced much more by the way they diffuse and are compressed. You've observed the flow of atmospheric gases as wind. Wind blows from high-pressure centers, its source, toward low-pressure centers. The kinds of pressure systems present determine the kind of weather a specific location experiences. There are many other familiar examples of fluid flow caused by pressure differences. A vacuum cleaner fan creates a low-pressure region inside the vacuum case, which causes high-velocity air to flow into the vacuum, picking up and carrying dirt with it. When you inhale, your ribcage expands and your diaphragm contracts, allowing your lungs to occupy a larger volume. The larger lung volume reduces the density, and thus the inside air pressure, allowing higher pressure air to flow into your lungs until the pressures equalize. Sucking on a straw placed in your favorite carbonated beverage reduces the pressure in the straw above the liquid. Atmospheric pressure pushes the drink up the straw and into your mouth. 8.9 Bernoulli's principle. Daniel Bernoulli studied the flow of fluids through pipes of different diameters that ran horizontally and vertically. He recognized that liquids like water were incompressible, but gases were highly compressible, though both could flow through pipes. He knew from Pascal's work that the pressure of non-moving water in a vertical pipe was related to the height of the water. Water higher in a pipe had lower, static pressure than water at the bottom of the pipe. He verified that water in straight, smooth pipes flows from higher to lower pressure. But he also discovered that the total mechanical energy of flowing water was conserved. In other words, the total kinetic and potential energies of a small volume of water, say a cubic centimeter, would change in predictable ways with pressure as the water flowed through a pipe. After experimenting, Bernoulli constructed the following model for an ideal fluid: P1 plus KE1 plus PE. 1 equals P, 2 plus KE, 2 plus PE2, where the subscripts 1 and 2 indicate two different points within a flowing fluid confined inside a pipe. A flowing ideal fluid in Bernoulli's model has the following properties. It is incompressible. Its density is constant. It flows smoothly with no turbulence. The speed of the fluid at a point in the pipe does not change with time, though its speed at different points in the pipe can be different. Friction has no effect on the fluid. The equation is a simplified form of what physicists call Bernoulli's principle. Most liquids and even slow-moving confined gases obey these conditions. The model helps scientists and engineers make predictions about the properties of flowing fluids. Let's look at a few special cases. When an ideal liquid flows through a horizontal section of a pipe, its potential energy remains the same, and the two PE terms in Bernoulli's equation cancel out. If we ignore friction, then the fluid's speed is constant, and the two KE terms cancel. Thus, we can predict that the pressure in a flowing ideal fluid in a horizontal pipe is everywhere constant. However, if we raise the downstream end of the pipe, the potential energy of the fluid increases as it rises in the pipe. To conserve energy, both the static pressure and the rate of flow in the entire pipe decrease. The greater the rise of T the pipe, the lower the pressure and the lower the flow rate. You may be able to observe this if you have a multiple-story house. Water pressure in the second-floor shower is lower than in the first-story sink. Many water companies use fluid potential energy to supply water at useful pressure to communities by building large water storage tanks on nearby hills. This is Bernoulli's principle at work. You may have noticed that when you hold your thumb over the open end of a garden hose and turn on the water squirts out far faster than when it flows out of the hose unhindered. Bernoulli's principle explains this as well. We can assume that the water's potential energy inside the hose just behind your thumb is the same as it is after it escapes. So the only factors that change are pressure and water kinetic energy. Water pressure inside the hose is much higher than outside atmospheric pressure when you hold it back with your thumb. According to the law of conservation of mass, the mass flow rate of the water inside the hose must be equal to the flow rate of water outside. To conserve kinetic energy, as the water passes by the constriction of your thumb, the water has to speed up, squirting out of the hose. The arrows in the equation below show the changes to the pressure and KE terms. P inside plus KE inside equals down. P outside plus up, KE outside. This happens in any constriction in a pipe containing a flowing ideal fluid. To conserve mass flow rate, the fluid speeds up in the smaller size pipe. See Figure 8-28 on the previous page. As the flow increases through the constriction, liquid pressure drops because pressure is exchanged for kinetic energy to conserve matter and energy throughout the system. Some liquid flow meters use this principle. A flow meter is a pressure gauge connected to a specially designed constriction in the pipe called a venturi. The gauge measures the change in liquid pressure between a normal flow point of the venturi and its greatest constriction. The pressure difference is proportional to the flow rate, which is indicated on graduated scale. When we imagine fluids flowing in pipes, we usually think of liquids. However, gases also can flow in pipes as well as around objects. Early physicists studying fluid flow noticed that gas pressure drops as velocity increases. The effect, however, is not as dramatic as that observed in liquids, because gases are compressible and tend to be far less dense than liquids. Even so, in the 1800s, several researchers with the objective of building human gliders began investigating how air pressure differences around a bird's wing contribute to flight. 8.1 The Coandă Effect. Many people believe that the only forces responsible for generating the supporting force or lift on an airplane wing are the pressure differences predicted by Bernoulli's principle. But this idea ignores Newton's laws of motion. In 1934, the Romanian physicist Henri Coandă discovered that fluids flowing close to a curved surface follow the shape of the surface rather than a straight path. This effect is caused by the viscosity within a flowing fluid, which tends to drag adjacent portions of the fluid with it. Figure 830 illustrates how the Coandă effect can divert the path of water flowing around a cylinder. The same principle applies to leaf-shedding roof gutters, which allow rainwater to flow into them without trapping leaves. The water flows around the curved surface and drips into the gutter. The leaves are too stiff and heavy to follow the curve with the water and fall to the ground. The Coandă effect is responsible for most of the lift in an airplane wing and other airfoils. The wing's motion through the air creates a downward force in the air above the wing. This force diverts large quantities of air from above the wing downward. What does Newton's third law require? The air must exert an upward reaction force on the airfoil lift. This is the force that supports an airplane. Garden hose chemical sprayers, artists' airbrushes, and some perfume aspirators use the Coandă effect in conjunction with Bernoulli's principle. In these cases, air or water is directed across the open end of a tube inserted in a liquid. This rapidly moving fluid flows over the tube end, creating a low-pressure region compared to the air pressure on the liquid. The liquid is forced up the tube and mixes with the fluid flowing by it. The chemical, paint, or perfume mixture sprays from the nozzle of the applicator.